Okay, good morning. Thanks, Adrian, for the introduction. I come from sunny Spain to sunnier UK, which is strange. It's a nice surprise. And yeah, Adrian said I come from INDEA Materials Institute, which is we are a network of institutes in Madrid. We are focused on materials, obviously, but there is like in there we have nanoscience, network, food, energy, a lot of things. So we're like a public institute. We're a non-profit organization, but we hold a lot of PhD students. We have a lot of collaborations with universities in Madrid. And without further ado, I'm gonna start because in the interest of time. I'm gonna talk about two different topics. We'll start with some pushing tests, and then in the final short part, I will present something on high entropy alloys for testing higher temperatures. So let's see if this works. So let's start with some pushing tests. Well, as we all know, fibers are used as reinforcements in polymeric matrix to, in order to improve the properties of the composites. So composites are widely used in the aeronautical industry, and it is the interface here that dictates how the two materials complement each other and in what way. Okay, so it's very important to know the strength of the interface between the fiber and the polymeric matrix. And yeah, we have some two examples how sometimes, in many cases, it is the interface that fails first. Okay. Now, these CFAB carbon fiber reinforced polymers are widely used in the aeronautical industry. The A380 has 50% of composite material, okay, by weight. And the problem with this is that the material certification can take up to 2 years, especially for polymers that age under different environmental conditions of humidity and temperature. So the industry is considering more and more doing virtual testing. That is a multi-scale testing, that can speed, you can reduce the experimental campaign, okay? And it takes much shorter time. We go up to 2 years to, using this virtual testing within this multi-scale simulation framework, and this one, okay, I'm not gonna give you any detail because I could explain here like ages, but you can find, information here, and it all starts at the micro level, okay, from the computational micromechanics. We start with the properties of the matrix, the interface, and the fiber. So we'll talk especially about pushing. So what the simulation people do, they, they construct this three-dimensional finite element model of the representative volume of the composite in order to predict the ply or the laminate strength. Okay, so we need to fit this with the properties of the matrix, the fiber, and the interface. Some properties are taken from literature, but some of the properties you really need to measure the properties in situ in the actual laminate, in the actual ply. Okay, so when I talk about in situ experiments, that means that we are doing the experiments in the real composite. Okay, in the cross section of the real composite. So for fiber pushing test, we're going to use nano-indentation. And I will just mention briefly the characterization of the polymeric matrix, okay, to get the elastoplastic properties of the matrix. For the plastic properties of the matrix, obviously, we can use, normally, indents are placed in resin pockets where we have a lot of resin. And, go here, and we can obtain the yield strength, we obtain the apparent hardness and the modulus, and from that one, there is some work that we can get the yield strength of the matrix, okay, in situ, taking into account all the residual stresses that, we cannot test the matrix itself, okay, we have to test the real matrix in the composite material by just doing indentations, okay, here. Or we can also do micropillar compression, we can create feed micropillars in the resin pockets, but we can obtain directly the stress strain curve. The problem with this one, of course, is feed damage. You create a stiff skin around the polymer, so it's not easy. But I mean, there is some alternatives to indentation. Again, you have to use a specific techniques for this. And we are going to move now to the interface characterization. Okay, two in situ techniques. We can either do push out or push in techniques. In push out, okay, we take the flat punch and we push out individual fibers. Problem with this is that the sample preparation is very tedious. Okay, you need a thin membrane of about the thickness of the diameter of the fiber. Okay, the fiber is 5 micron, so 1.5 to maybe 10 microns. So it requires a lot of sample preparation, not easy, and you can also relieve some of the stresses. You know, people have done this successfully, and you can get basically the critical load there. So it's easy to get the debonding, the strength. And the other alternative is pushing. Okay, pushing is like push out, but you do this in the bull cross section. So you just need to polish the surface, and you just push individual fibers. And I will tell you a little bit more about what are the issues with this technique. And what you get is you get a low displacement like this. Okay, when you get in the pushing curve, of course, you have a linear part due to the elastic deformation of the fiber and the surrounding environment. And this ends in the non-linear part, where we have a deviation from linearity, and we have some sort of critical load, okay, that marks the debonding on the interface. And this can be analyzed, what is called the shear lag model, to calculate the interface shear strength. And I will tell you a bit, because this depends on the stiffness, critical load, radius of the fiber, and elastic modulus of the fiber. Okay, it's a simple approximation, and I will tell you a little bit about the problems that you are using this model for this. So we move just to the experimental procedure. Okay, sample preparation, the tests themselves, determine the critical load and the interface shear strength. Okay, sample preparation. You know, sometimes we get these thick samples in a wedge shape, and this is how we're going to test that. So we need to, sometimes you need to rectify the back of the sample to make it plane parallel with the surface. You need to have a nice polished surface, not mirror-like, but you need to see the fibers, okay? And for example, for wet conditions, sometimes we get the samples in a wet envelope, and we need to put them into the climatic chamber for many days to reach saturation, water saturation level, okay? So we put them in a climatic chamber with 85% relative humidity and 80 degrees, and then we test the material. And we also do the test at 80 degrees, okay? That's the hot, wet conditions. So we mount the sample in the hot stage. Good thing about the nano test, it can accommodate large samples. That's a good thing, okay? So we can just place the sample there, and the important thing is that we can see the fibers, okay? So for this one, we use our nano test, platform 3. And good thing about it, we can hit the sample and the tip independently, and we can just carry out the test with the necessary loads for the pushing. So some of the experimental details, we use a flat punch with a 5 micron diameter. The fiber is around 6.5 microns, so you need to have a punch with a diameter which is close to the fiber. And I will tell you why now, okay? You cannot use like a 1 micron punch to push into the 5 microns, because you are going to cause plastic deformation, okay? So we use 20 nanometers per second, displacement rate, maximum displacement of 1 micron. And we are going to test fibers which are in this hexagonal closed pack configuration, like the top face of hexagonal closed pack unit cell. Because we need to do this where we have a constant surrounding environment, okay? It's not just going to test any fiber randomly. You look for this kind of fibers inside this hexagon. It's like a honeycomb structure. So this, for example, a pushed-in fiber, this one, you can see before and after the pushing. I like to have an image before and after to make sure I'm pushing on the right one. It has the test has a good accuracy. So once you have the good calibration, obviously, you can push. And this is another example on the wet sample. You can see a clearly debonded region around the fiber. Okay, so that's, I would consider that's a successful test. Okay, of course, in this case, I have a lot of fibers to choose from. Sometimes the volumetric fraction of the fibers is not as you expect. This is maybe 50, 60% volumetric fraction. You have less fibers, then more difficult. But normally you have enough to go around and do this test. And in some of them, we have done some AFM just to make sure that there is no plastic deformation on the fiber. So you can see this is the pushed-in fiber in this hexagon, and we can see some pile-ups and resin coming out, but there is no residual imprint on the fiber. Okay, so this is the pushed-in fiber here, and again, no residual imprint, which is good. Otherwise, you might have, this is on a glass fiber, so you have this plastic deformation. You need to take this into account in the analysis. I don't know how you do that, but just make sure that your diameter adjusts to the fiber size. Okay. Now some examples of these are actually the direct test results. Okay, what you get is obviously the load displacement. This is about 21 indentations. Okay, very good reproducibility. So you have the initial, a non-linear region here because of the accommodation of the contact between the indenter and the fiber. Then you have the linear region, which is the elastic deformation, and then you have the start of the non-linearity where the fiber matrix interface starts failing. Okay. This is for the wet sample. It was more difficult to find fibers, so had less reproducibility. And this is actually the test I did sometimes with 70 or 80 degrees, depending on what the customer wants. We normally do this test for Airbus or Excel. They want this pushing test now more and more. This is not like part of a research project, but sometimes I don't know. They say 70 or 80 degrees. I say whatever. Then I do 70 if I can choose. On the wet sample, okay. I don't know why you want to do that because when you heat and there the water will come out. But anyway, we do the test as fast as we can, and you can see still the reproducibility is good. Okay, for the hot side. Now from the load displacement curve, what you want to get is the stiffness and the critical load. Okay, the stiffness is just the slope of the linear part. We use our own Python script to do that. There is no standard procedure to get the stiffness and the critical load. You can do whatever you feel that is right. We use an iterative linear square feet of this linear part and then a distribution of the stiffness, and we get that. And for the critical load, we do a polynomial fitting, okay, with increasing number of, with different orders for the polynomial and several ranges of displacement, and then we take the derivative and the deviation from the previously calculated stiffness is less than 1%, we take that as the critical load. But you can select what you want. You cannot just do the 2% or whatever. It's up to you to get the critical load, okay? And this is what you get. We get the stiffness and the critical load for the three conditions. We look at the dry condition, wet, and hot wet, okay? We have the stiffness and the critical load. You can see it decreases for the wet condition and more for the high temperature condition. Now, we can use this shear lag model to get the shear strength of the interface. As I said, this is a first approximation, okay? Stiffness, critical load, the radius of the fiber, it goes to the cube, so you will get a very high errors. Ideally you should measure the diameter of each fiber that you pushed in, because they have different diameters. Okay, they can tell you it's 6.85, but then you can find fibers which are 5 microns. So ideally, I have taken just an average value, but it goes to the cube. So careful with that. And okay, this is the shear stress you get from this model. Okay. Okay, to refine this model, some people have done finite element modeling. Okay, taking a constant environment to take into account the surrounding environment and some thermal stresses as well, okay? And what they use, you can find some information on these two publications, and there is a correction for this shear stress that depends on also on this delta T, which is the difference between the curing temperature and the test temperature. Okay, you can take into account the thermal stresses and the surrounding environment. That's why we look for this hexagonal closed pack. Also, we make sure with this hexagonal configuration that the interface is aligned. These are unidirectional fibers. Okay, so with this hexagonal configuration, you make sure that it's more likely that the interface are sort of perpendicular. And at the end, you get the corrected shear strength, okay, by using this format. This A and B depend on the radius of the fiber, modulus, and this delta temperature. Okay, this is some simulation that some people have done. So the shear stress concentrates at the fibers, and then when we reach the critical load, most of the interface is debonded, and then we have the crack down to into the sample. Okay. And okay, the take-home message is that you cannot assume a perfect interface. Okay, the interface sometimes is controlling the failure of the composite material. Okay, we can see in this image. This is a mode 1 of deformation, and you will see some, the material is failing through the interfaces. Okay, like the same here. You can see some bonding there. Maybe a high temperature, what will yield first is the matrix, okay? But you need to measure the strength of your interface, okay? That's the, it's here, opening in here. Okay, for the second part, which is shorter, okay, I will try to speed up, just let me know. We go to higher temperature, okay, for high entropy alloys. Okay, as you know, high entropy alloys are now in fashion, because they can, especially these refractory high temperature, high entropy alloys, because they can increase the service temperature for some applications for combustion engines. They can increase the yield, they can yield superior efficiency for the combustion. Okay, and they were deposited by this direct energy deposition technique, which is good because you can, in the academic and industrial communities, they use this technique for in situ mixing, okay, to try out different compositions, okay, at one go, because you can change the powder types and the quantity of the powder to check different compositions. And these some Calfat simulations have shown that adding, for example, vanadium or titanium to this, in this case we have this refractory high entropy alloy, you can keep the BCC structure, okay? So eventually we will have the same BCC as the powders, okay? So these are some powders. They mix this powder with this vanadium powder, and these are the BCC of the powders itself. So this is the as-built structures. To me, they look like slabs from a graveyard. When they send me but they deposit this like layer by layer, okay, with different compositions. And you can see some micrographs here. There is some degree of porosity. I mean, a lot of dendrites. Let's say that there is a lot of microsegregation. It's not an ideal structure. It's a lot of heterogeneity in the compositions. Some unmelted powders also we can find. But anyway, I did the test in one of them. It keeps the BCC structure, okay, some preferential orientation for the 1110. The XRD spectra looks exactly the same as the powders, so we can keep the BCC. And I looked at these compositions for the nanoindentation. Okay, so I got this one. We have 4 different zones with different vanadium content from 0%, 11, 17, and 22. 4 different zones. So I get this. We get these pieces. This is the piece mounted with high temperature cement on the hot stage. Okay. Again, it's, you can accommodate large samples. It's placed. So I look at this. There's also already some indents here. Okay. And I use also the same platform with a cubic boron nitride indenter tip. Okay. In an inert gas atmosphere. As we know, it's important to control the thermal drift. Okay. Important to control the thermal drift and do this in an argon atmosphere at 700 degrees. Okay. We want to limit the oxidation, and we want to limit the drift. And these are some experimental parameters. I'll use a maximum load of 150 millinewtons, 10 seconds loading time, 10 seconds dwell time, 4 seconds unloading, and the thermal drift correction after 90% of unloading, a typical strategy used for high temperature. At least 7 indentation at room temperature, 350 and 700 degrees. Okay, this is room temperature, tip and sample, 700 degrees. Tip is red hot, okay? It's a cubic boron nitride. It's been used a lot, so I didn't want to go to push it to 800, just in case. But I thought 700 is already a good, nice temperature to test these alloys. Some indents, okay, there is no obvious signs of